In this lecture, we'll have a look at the variance of the OLS estimators. And we will do this for the simplest possible linear regression model, one where the Gauss-Markov assumptions are satisfied. So the setup is the following. We have a linear regression model with random sampling. We also have the Gauss-Markov assumptions. That is, we have exogeneity and we have a constant conditional variance of the error terms. From this data generating process, we can estimate beta 1 and beta 2 using the OLS estimators B1 and B2. And since we have exogeneity, we know the expected value of B1 and B2. The expected value of B2 is beta 2, while the expected value of B1 is beta 1. They are unbiased estimators. So in this section, we'll look at the second moment of the OLS estimators, namely the variance. So before presenting these results, just let's think a little bit about what we mean by the variance of the OLS estimator. So consider this simple example. In this cell C5, I have just simulated a random number from the normal distribution, and the normal distribution has this expected value and this variance. So I can think about performing an experiment by clicking the F9 button, and each time I perform an experiment I get a random number. Since the expected value is 0, these numbers are sort of sometimes bigger than 0, sometimes smaller than 0, and these random numbers also are drawn from a specific variance. So in this case I have a variance of 1. That means that there's a 95% probability that the number shown here will be between plus minus 1.96. So in about 95 out of 100 F9s, I will get a number between plus minus 196. And in about 1 out of 20, I will not, like here, for example. If I increase this variance, I will also increase the spread of these random numbers. So if I do a sigma of 2, then these random numbers will have a bigger spread. So now it's more likely to get a number outside this plus minus 196. And the bigger I make it, the bigger is the spread in these numbers. This expected value is still 0. Now the idea for the least squares, the OLS estimator, is exactly the same, just a little bit more complex. We can view this number in cell A11 as a random number from a random variable, just like a random drawing. And we can ask ourselves, what's the expected value of the random variable generating these B2? Well, we know the answer to that. It's beta 2. It is 2 under the exogeneity assumption. So this number is a drawing from a random variable with expected value 2. And we had a discussion of that, because as we F9 this experiment, we get somewhere plus minus 2, sometimes above 2, sometimes below 2. But we can take one step further and we can say that these numbers, or this number in cell A11, is a drawing from a random variable with a specific variance as well. And it turns out that we can actually calculate the variance of the random variable generating this B2. We can calculate that variance, and it will turn out to depend on the standard deviation of the error terms, and it will depend on the sample variance in the x variable. So we're not going to prove it, but you can actually prove it. It's not that difficult. You can show that the variance of B1 conditionally on the x data. So it's the variance of the intercept for the particular data that we observe is given by this formula. The variance of the slope parameter b2 conditionally on x is given by this formula. This particular notation, VAR of b2 conditionally on x, is just shorthand for the variance of b2 conditionally on or given all the x observations, x1, x2, all the way to xn. Again, it's the slope parameter b2 that's typically the most important one in econometric analysis, so let's focus on that one. You can see that it's equal to sigma square, which is the variance of the error term, divided by the square deviations of the x's from its sample mean. You can see that the denominator is just n minus 1 times the sample variance in x. So in a simulation study, when everything is known, including sigma square, we can actually calculate this variance. So let's do that in this cell A14. The variance of B2 given x is equal to sigma square. Well, that's in B4. So B4 squared divided by, and here we should have n minus 1 times the sample variance in x. N is 20, so 19 times the sample variance, var dot s, of the x data. Like that. And then n parentheses. And so this is the variance for this particular data set for x. So we can now view this number here, 2.08, as a random number that has been drawn from a random variable with this expected value and this variance. Since the variance of b2 conditionally on x, the variance will change when I draw new data, and that makes sense because it's the variance of b2 for this particular data set. It's different for different data sets. But we can see that this variance will tend to be bigger if I increase the standard deviation of the error terms. If I increase this to say 4, then this variance tends to be much bigger. And now consistently we have more spread in this B2. Now B2 will be on average typically further from the expected value 2, which we can see by F9ing. One more thing we should do before we finish is to paint this number red. That's kind of important because this is actually a number that would not be available to us as econometricians. And that's because it's calculated using both green and red numbers. I've used the x data, that's fine, but I have also used the sigma here, which is not known to us as econometrician. So that means that this variance is actually not known to us, but it's still there, it still exists, just like the variance of the error term exists even if we don't know what it is. So there's a couple of things that you should notice about these variance formulas, and in particular it's the second one that's important. And these things are as follows. The name, first of all, they're called the OLS Gauss-Markov variance formula. And the reason we typically call them OLS Gauss-Markov variance formula is because they're only valid if the Gauss-Markov assumption is satisfied. Remember, we only need exogeneity for the OLS estimator to be unbiased and consistent. it is not enough with exogeneity to have the variance formula. This is not correct unless we also have homoscedastic errors. And if you think about it for a second, that kind of makes sense because this symbol, sigma square, that only exists when we have the Gauss-Markov assumption. Then sigma square is this common variance of the error terms. If we have heteroscedasticity, then all the error terms have different variances and there is no sigma square symbol in that case. So we call them the OLS Gauss-Markov variance formulas. The second thing is the notation, which we mentioned a little bit earlier, that this variance of B1 conditionally on X, well, X is just a symbol that doesn't really exist in the sample, so it's just a shorthand notation for the variance of B1 conditionally on all the X data, given the observations for my explanatory variable. Emphasizing again why we painted that red. It is unknown to us because it depends on sigma square, which is unknown to us. Looking at the formula for B2, we see that we have a sigma square in the numerator. That means that the variance of B2 will depend positively on sigma square. If I increase sigma square, I will also increase the variance of B2. And that should be intuitively clear. If you increase sigma square, that means that you introduce more variance into the error terms. That in turn means that the scatter plot of the data is now much more spread out and the individual points are further from the true regression line. And that in turn means that we have a harder time estimating beta 2. So we'll get a larger variance for B2. A large value for a large value for the variance of B2 is obviously bad news because it means that the precision or our certainty in the estimate that we have come up with is very low. You can also see that the variance of B2 depends negatively on the sum, and this sum is just a scaled version of the sample variance. So you can see that the variance of B2 depends negatively on the sample variance of X. So the higher the sample variance in X, the lower the variance in B2, and the better our estimate is in general. That too is important because it means that if you want to have nice precision in your estimate of beta 2, it is better if your explanatory variable, your X variable, displays a high sample variance. That is, your dependent variable should have a large spread and not be closely bunched together. So these are the final points. The higher the sigma square, the higher the variance in B2 and the worse we are. The higher the sample variance in the X data, the lower the variance in B2 and the better we are. The better off we are, I should say.